Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. In this lecture, we are going to learn about the concepts related to standing waves. We are going to have the definition of standing waves and how they are formed. Let us see the session outline for today's lecture. In this lecture, we are going to learn standing waves or stationary waves for fixed ends and free ends, and also the different modes of vibration. What are standing waves and how they are formed? Let us start our lecture with the definition for it. Let us see the definition. When two progressive waves of same amplitude and wavelength traveling along a straight line in opposite directions superimpose on each other, standing or stationary waves are formed. The phenomenon results in the redistribution of energy. Energy is either added together at some points and cancelled out at some other points. So, this is the definition for standing waves. You could have noticed one condition that was specified in the definition. They should have the same amplitude, same frequency or wavelength, and the key point is they should travel in opposite direction. What does that mean? One wave has to travel like this, the other wave has to travel in the opposite direction, and they both have to superimpose with each other. In that situation, we have a special kind of wave formed, that is standing wave. When we say the superposition, we normally consider the waves traveling in the same direction, one wave like this and another wave also in one direction, and the effects have been learnt. But when the waves travel in the opposite direction, a peculiar kind of wave pattern is formed. That wave pattern is called standing wave, or it is also called stationary wave. Why it is called stationary wave? Because it is not progressing. The energy is not getting transported in one direction, but rather it is redistributed. So, we shall learn more about what are standing waves. For getting the understanding, we need to have the mathematical expressions. So, let us do an analytical method for obtaining the final expression for standing wave. We have to choose two waves which travel in opposite direction and mathematically add them to get the final expression. So, this is the way of approach for arriving at the final expression for the standing wave, which we call as the resultant wave. Let us see how the analytical method is adapted. Let us consider a progressive wave of amplitude A, angular frequency omega and wavelength lambda traveling in the direction of plus x axis. We have y1 is equal to a sin omega t minus kx. This wave is reflected from a free end and it travels in the negative direction of x axis, and that is represented as y2, which is equal to a sin omega t plus kx. This is the expression for a wave traveling in the negative direction of x axis. We know that omega is 2 pi nu, here nu is the frequency, omega is called angular frequency. Similarly, k is equal to 2 pi by lambda, lambda is wave length and k is wave number. We have specified the two waves are obtained by method of reflection. It could be done in several ways. Two independent waves travelling in opposite direction also can be added together. By reflection, we can get a wave travelling in the opposite direction, that is one of the methods. We have lot to discuss about the reflected waves towards the end of this lecture. Now, we will proceed further with the analytical method of simplifying the superposition term. Let us typically add the two waves to arrive at the final expression. Let us proceed further. According to the principle of superposition, the resultant displacement is written as y is equal to y1 plus y2. We are adding them. So, this is the resultant displacement y, this is y1 term, this is y2 term, and we take a common, and using the trigonometric identity shown here, we can proceed with the simplifications further. The final expression is obtained for the standing wave like this: y is equal to a sin omega t and cos kx. Here we can bring in the cos kx term along with the amplitude, because amplitude is a spatial variation. Here we have x, which is also a spatial term. So, we have brought them together and written in this modified way, which has a modified amplitude a cos kx as an amplitude and a sin omega t as the time varying factor. But when we have a look at this final equation for standing wave, we do not see the term which represents the wave. Which term represents a wave? The omega t minus kx, that is only going to represent a wave, but that is missing here. We have only omega t. Where do we have this omega t term alone? We have it only in the case of oscillation. When we have omega t plus or minus kx, then only it is called a wave. So, the equation finally we have obtained is an equation for only the oscillation, but of course, the amplitude is getting modified in terms of space x and also in terms of time t. So, it is simply a vibration which is varying at various points governed by the spatial position and also the temporal term time. So, let us have the equation once again and understand it is not representing a progressing wave. That is why it is called a standing wave. The above equation is the equation of vibration that is varying with respect to position x and time t. This is not the equation of progressing wave, because the terms omega t minus kx or omega t plus kx are missing in them. Now, we will take up the special cases for discussion, because the spatial variation and also the time variation are going to decide the final displacement. So, let us take the two cases and see how the standing wave pattern appears. Let us take the discussion further. Special cases which discusses about changes with respect to position. In the previous expression, at points where x is equal to 0 or lambda by 2 or lambda or 3 lambda by 2, the values of cos kx will become plus or minus 1 alternatively. The amplitude is plus or minus 2a. At these points, the resultant amplitude is maximum, and those points are called the antinodes. Similarly, at points where x is lambda divided by 4, 3 lambda divided by 4, 5 lambda divided by 4, etc., the values of cos kx will remain 0. Thus, the amplitude is also 0. The resultant amplitude is 0 at these points they are called nodes. So, we have two special cases where the amplitude seem to be maximum and other points the amplitude seem to be 0. So, these are the two extremums, but this is happening at different locations. So, different positions of x. So, what is the conclusion? We have antinodes and nodes alternatively appearing in the case of standing wave. Shall we have a look at the way in which the standing wave pattern is formed? Node and antinode. The distance between any two successive antinodes or nodes is equal to lambda divided by 2, and the distance between an antinode and a node is lambda divided by 4. We will be seeing these meaningful when we have a look at the diagram, and we will finish the discussion for the changes with respect to time. That is a third special case. When t is equal to 0, capital T divided by 2. What is the meaning of capital T here? It is a time period. So, it is capital T 3 t by 2 and 2 t etc. Then the sin omega t term will become 0 for these values of t, the displacement is 0. Similarly, when the time is time period divided by 4, 3 t by 4, 5 t by 4 etc., then the sin omega t will become alternately plus or minus 1 and the displacement seem to be maximum. The time also decides the position. So, the conclusion is with respect to x there are fixed maxima and minima. The time also is having a role in deciding them whether the value of the displacement is maximum at that instant or minimum at that instant. So, let us have a look at the standing wave pattern now. So, this is the standing wave pattern. We have a picture shown here. This represents a wave travelling to the right, a wave travelling to the left. They superimpose and produce nodes and antinodes here. Node is the point where there is no displacement. It is appearing alternatively to the antinodes. Antinodes are points where the displacements are maximum, and this is shown here as an animation. The two waves which are travelling in the opposite direction interfere with each other to produce the standing waves. This is a static picture and this is a animation which is varying. The key point to notice here is it is not progressing. See, where the maximum is occurring or that is happening at the same position, it is not moving forward or backward. The value is changing between the positive and negative, the displacement is still there, and where there is no displacement, it is no displacement forever, it is not changing with respect to time at all. So, this is the meaning of standing wave. The progression is not happening, the energy is not transported forward, but it is redistributed. So, there are some characteristic features, key points we need to keep in mind as far as the standing waves are concerned. When we say standing wave, we should not be carried away by the word wave present in it. It is the vibration which remains static, it is confined to space, and with respect to time the variations are happening. So, let us see the key factors. Characteristics of standing waves. The waveform remains stationary. Nodes and antinodes are formed alternately. The points where displacement is 0 are called nodes and the points where the displacement is maximum are called antinodes. Pressure changes are maximum at nodes and minimum at antinodes. Why the pressure change is maximum at antinode? At antinode only the vibrations are happening to the maximum extent, and at nodes the vibration is not happening at all. So, the pressure change is not happening, pressure change is maximum at antinodes. Let us proceed further with other characteristics. All the particles except those at nodes execute simple harmonic motion of same period, amplitude of each particle is not the same. It is maximum at antinodes and decreases gradually and is 0 at the antinodes. The distance between any two consecutive nodes or antinodes is equal to lambda divided by 2, whereas the distance between a node and its adjacent antinode is equal to lambda divided by 4. The last point has been shown as the diagram itself. Let us proceed further about the redistribution of energy. So, the other key factors are also shown here. The velocity of the particles at the nodes is 0 because there is no vibration at nodes. It increases gradually and is maximum at the antinodes. There is no transfer of energy, but energy is redistributed. At nodes the energy is 0 because no vibration, and at antinodes the energy is maximum. So, about velocity there is a variation happening. Each particle is having different velocity, but all of them are varying in unison. They have the same time period when they vibrate. What other key factors we have? Let us proceed with the characteristics of standing wave. All the particles of the medium pass through their mean position simultaneously twice during each vibration, upward and downward. That is why the term twice is used. Particles in the same segment vibrate in the same phase, and between the neighboring segments the particles vibrate in opposite phase. When we say segment, it means a complete loop between two nodes, we call that as a segment. All these key factors or characteristics of standing waves could be understood when we have a look at the animation which was just shown, how alternatively the movements are happening, like this. So, one section, alternate section has the upward motion, the other alternate section will have a downward motion when the standing waves have vibrations in them. The animation will give us a greater insight of the movement of particles. So, in standing wave the energy is not transported in any direction, but it is redistributed. Now, we need to discuss about the technique of making two waves travel in opposite direction. It is done by method of reflection. When a progressing wave is stopped by a stop or a block, the wave would be reflected backwards, and thus we have the two waves which are travelling opposite to each other. Rather than having two separate waves travelling in opposite direction, one single wave which is travelling in one direction continuously, if it is reflected back, we have two waves which are propagating in the opposite direction. That too, it is easy for us to make them interfere because the vibration will happen in the same line. So, let us see what are the implications we have when we have the reflection happening for the progressing wave. The standing wave by reflection is one technique. In musical instruments like sitar, violin, etc., sound is produced due to vibrations of the stretched strings. Different modes of vibrations of the string are formed, which is rigidly fixed at both ends. When a string under tension is set into vibration, a transverse progressive wave moves toward the end of the wire and gets reflected. Thus, stationary waves are formed. Reflection produces stationary waves. So, that is the key point we have to keep in mind. Let us see the implication of the reflection. The fixed end, when we say the string is fixed between two ends. Sometimes one end could be a fixed end or it could be a free end also. Let us see what they mean. There is a phase change of pi between the onward and reflected waves at the fixed end, but at the free ends no such phase change occurs. So, that is the implication of the reflected wave when it is travelling in a single stretched string. The left hand side diagram shows the fixed end here. See, the wave is travelling and it is trying to lift this part also up, because each segment of the string is lifted up when the wave travels, and it is trying to take this part also up because it is rigidly fixed. According to Newton's third law, it exerts a force on the flexible string downward. The string tries to take this point up, because it is not responding, it pulls the string down. So, there is a phase difference. What is the meaning of phase difference here? A crust becoming a trough. Between the crust and trough, the phase difference is pi, or it is 180 degree. What happens when the end is a flexible end, which is a free end? We call that as a free end. What will happen? Let us have a look at the picture. See, in the case of free end, it is freely lifted up. So, the reaction force is not there, because there is no reaction force at all. So, it is reflected backwards as the same crust. Crust is reflected as the crust. There is no trough formed here. So, this point we have to keep in mind when we consider the reflection happening when a wave is travelling in a string. These two have two different implications. The fixed end could be the node and a free end could be an antinode, because the free end is vibrating freely. Where the vibration happens maximum in a standing wave pattern? Only at the antinodes. So, these are the 2 points we have to keep in mind. When the point of reflection is fixed, it is the position of a node. When the point of reflection is a free end, it becomes the position of the antinode. So, accordingly the wave pattern will be formed. Now, instead of fixing the ends or keeping it free, if it is continuing with a different medium, maybe a different density, what will happen? So, let us take it up for discussion. In the case of a boundary that is there, what will happen? See, here there is a thin string and there is a thick string attached to it afterwards. When a pulse is allowed to travel at the boundary of the two strings, there is a reflection happening and also there is a transmission happening. The transmission is having the same crust, it is not getting modified, but look at the reflected wave, the crust becomes a trough. Whereas on the other side, the reverse, the original pulse is produced on the thick string, that is a denser material, and on the right continuation is a very thin string which shows a rarer medium. So, here there is no phase reversal, the reflected wave is also getting reflected as a crust, the transmitted wave is part also is travelling as a crust itself. There is no trough formed at all, but here there is a trough. So, in conclusion, we can have one tabulation which will give us consolidated statement. Let us have a look at the tabulation. Here is the medium. When the wave is travelling from rarer medium to a denser medium, the reflected wave alone has a phase change of pi and the transmitted wave there is no phase change. On the other hand, if the wave is travelling from denser medium to a rarer medium, there is no phase change both in the reflected wave and also in the transmitted wave. Only in this peculiar case, wave has to travel from rarer to denser medium, and that too only in the reflected wave there is a phase change of pi. We need the reflected wave for forming the stationary wave pattern or standing wave. So, the phase change of pi is occurring when it is travelling from rarer to denser, and no phase change in the case of denser to rarer. So, accordingly, we have to introduce this phase change pi in the reflected wave and then do an analytical treatment. When we do that, we will be able to get the node at the fixed end, which is the case of reflection happening when wave travels from rarer to denser, and free end is the example for wave travelling from denser to rarer medium. The free end is allowed to vibrate. So, that will decide whether the node is formed at the end or antinode is formed at the end. So, whether the end is a fixed end or free end is very important for us for deciding the nature, whether a node or antinode is formed. Hope we have got a better understanding of what we have discussed as nodes and antinodes. Now, we will have a visual that will give us a greater understanding of how the modes of vibrations are happening. Let us have a look at this picture. See, when we have a string, there are two ends. If both the ends are free, the antinodes are formed at the ends, at both the ends. When the two ends are fixed, we have the nodes formed at the fixed ends. See, here also the nodes are formed. When one end is a fixed end and the other end is a free end, at the fixed end the nodes are formed, at the free end antinodes are formed. We will have to keep this point in mind. Fixed end we will always have nodes, free ends we will always have antinodes in the positions. And in the picture that we have shown, we have seen different modes of vibrations have also been shown. So, it opens up another topic for discussion, what are called nodes, modes of vibration. Let us have the picture once again, with which itself I will explain the meaning of modes. Here we have one loop formed. Take up this part for the discussion. When we vibrate it at one condition, one loop is formed for a particular length, and in this case there are two loops formed. Accordingly, here also we have the loops formed. I will show it with enlargement of the picture. So, these are the meanings of modes of vibration. Here it is a quarter wavelength and here it is 3/4 wavelength. When we compare it with here it is half wavelength, here it is one full wavelength, and accordingly we have different types of vibration happening for a given length of the string. A particular length can vibrate with different modes possible in them. I would like to show one more animation which will give a greater understanding of the different modes of vibrations possible in a stretched string. Have a look at it. See here, one after the other, there is only one loop formed. This is a particular mode of vibration. Here there are two loops formed, here 3, 4 and so on. All these vibrations are happening with one thing constant. Have you noticed that all the vibrations are occurring for a particular length? The length is not varied. Only for a particular length the different modes are happening in them with one loop, two loops, three loops and so on. So, we will have to discuss about the different modes. What is the meaning of mode itself? We will discuss about them in the coming lectures, but I have shown the types of vibrations possible for a given length. So, let us see the summary of today's lecture. In this lecture, we have seen the concepts of standing waves, stationary waves with fixed ends and free ends, and also the definition of modes of vibration we have seen. Let us test our understanding by answering these questions. Define standing waves and explain how they are formed. Obtain the expression for standing wave by analytical method. Give the characteristics of standing waves. Explain the phase changes happening at free and fixed ends of a stretched string. So, with this I would like to wind up this lecture. Thank you for watching.